Hi everyone! So for today's meeting here in Statics of Rigid Bodies, we're now going to discuss the equilibrium of parallel force system. So for this topic, you must be able to attain the following intended learning outcomes. So the first one is students must be able to compute reactions of supports of parallel force system in equilibrium. The second one is you have to enumerate different types of loads, identify the different kinds of beams, based on supports, compute the reactions of the supports of the beam, and compute the reactions of cables in frictionless pulley system. Okay, so to start the discussion, the conditions of equilibrium for parallel force systems are determined from the conditions necessary to create a zero resultant. So these are the equations that we're going to use in solving for equilibrium of parallel force system. So it can be one moment equation, okay, and that will be equal to zero, and one summation of forces, and that will also be equal to zero, since here in this topic, this is equilibrium. So meaning to say the resultant of that parallel force system, okay, is zero. Okay, and if the resultant is zero, the summation of forces, whether horizontal or vertical, will just be equal to zero. And the summation of moment at any point, that will also be equal to zero. So these are the two equations that we're going to use in solving for systems, okay, of parallel forces, okay, in equilibrium, okay, or okay, we can actually have a choice, okay, if what equations are we're going to use. So we can also use two moment equations. Also, we can use summation of moment at a specific point that will be equal to zero, and summation of moment, okay, at another point, or at about another point in the system, and that will also be equal to zero. So it's up to us what are the combination of equations that we're going to use. So it can be either summation of moments, okay, and one equation for summation of moment and one equation for summation of forces, either horizontal or vertical, or it can be both summation of moments. Okay, so it's up to you, no? Ayun. Anyway, so it can be applied to beams and frictionless pulley systems. So this topic, okay, equilibrium of parallel force system, in real life, okay, we can apply this in computation, okay, of a force system, okay, that is created by beams and frictionless pulley system. So these are some examples of beams, no, that we're going to discuss here, and frictionless pulley system. So this is an example of a frictionless pulley system. So we're going to use the concept of equilibrium of parallel force system for such bodies, no? So let's discuss further about beam. So beam, it is a part of a structure, or it is a structural member that carries a load that is applied transverse to its length. Transverse meaning to say that the load is not applied along the longitude of the length of the member. Okay, because if that's the case, that structural member might be a column. Okay, it's not a beam. Okay, so again, a beam, it carries a load that is applied transverse to its length. Okay, and um, so beams are also used, okay, to support floors and roofs. No, as you can see here in this figure, these are actually beams. No, so these are the structural members called beams. No, and these are girders. No, so girders actually are also a kind of a beam. No, so but anyway, so these beams, okay, these are the structural members that will actually support, okay, the floorings that will be put here, right? Let's say on this area, no, on this floor. So the flooring will be put here, and that flooring, it will be carried, okay, and supported by these beams. Okay. So also, beams are also used to support roofs, no? Yung mga roof trusses. Okay. So beams are also used to support those, no? Ayan. And also, beams can also be called floor joists, stringers, floor beams, or girders. Okay, and the loads are initially applied to a building surface, that is floor or a roof. Okay, and the loading generated by the applied floor or roof, okay, it will be transferred to beams. Okay, so again, it is the beams, okay, who will support, okay, the floors or the roof, and after that, okay, the loading that is carried by the beam, it will be transferred. Okay, it will be transferred to another structural member, which is actually the column. Okay, so from flooring to beam, and the structural member that support the beam, okay, will be the columns. Okay, so that's how it works now for structural members. Let's talk about now the different types of beams. So according to determinacy, a beam may be determinate or indeterminate. Okay, so for statically determinate beams, okay, these are beams in which the reactions of the supports may be determined by the use of the equations of static equilibrium. The beams shown below are examples of statically determinate beams. Okay, so these are the examples of statically determinate beams. Okay, so these are cantilever beams or cantilever beams, no? So cantilever beams are supported by a fixed support at one end. Okay, and we also have here a simple beam or a simply supported beam. So a simple beam or a simply supported beam, it is supported by one roller, okay, and by one hinge. Okay, so that's simply supported beam, no? And also we have here overhanging beam. So for overhanging beam, there's just a portion, okay, of the beam that is overhung, no? So that's why it's called overhang beam. And its support is also the same with your supports for simple beam, no, or simply supported beams. Okay, so its difference is that just there is a portion of the beam that is overhung here. That's why it's called overhanging beam. Okay, so these are the types of beams that we can solve, okay, here in statics of rigid bodies. Okay, so the second type of beams, which are the statically indeterminate beams, okay, it will not be covered, okay, by this course. So these are the only types of beams that we're going to discuss, okay, and solve here in statics of rigid bodies. So the second type of beams are called statically indeterminate beams. So if the number of reactions exerted upon a beam exceeds the number of equations in static equilibrium, the beam is said to be statically indeterminate. In order to solve the reactions of the beam, the static equations must be supplemented by equations based upon the elastic deformations of the beam. Okay, so these are the examples of statically indeterminate beam. So these are prop beam. So a prop beam, it is fixed supported at one end and either roller supported or hinge supported at one end. No, so this is called a prop beam. Okay, and we also have fixed beam or fixed restrained beam. No, so meaning to say the supports at both ends of the beam are fixed supports. Okay, that's why it's called fixed beam or restrained beam. And also we have continuous beams. No, so for continuous beams, okay, we have here supports, okay, within the span of the beam. No, so we have intermediate supports here. Okay, and these three types, okay, of beams, okay, we will not discuss this in our course, no, for statics of rigid body. So this will be discussed in your theory of structures, no, but these are the second type, okay, of beams, no, so they are statically indeterminate beams. So let's talk about now the different types of loading that we will frequently encounter, okay, in the beams that we're going to analyze in this topic. Okay, so loads applied to the beam may consist of a concentrated load or load applied at a point. That's why it's also called point load. Okay, we have here uniform load, uniformly varying load, or an applied couple or moment. So these loads are shown in the following figures. Okay, so as you can see here, these are examples of concentrated load. So this load P1, load P2. So these are concentrated or point load. Okay, so we also have here uniformly distributed load. So uniformly distributed load, the loading is distributed uniformly, okay, along the length of the or on the length of the beam, no. Okay, so also we have here varying load. So Varying loads, it also includes trapezoidal loads, no, not just triangular loads. So it also includes trapezoidal loads, since that type of load is also varying, no, from a specific intensity to another intensity, no. So those are also uniformly varying load. And we also have here an applied couple or moment. So in this case, this moment or couple, okay, it is part of um, it's like a applied component, no, on the force system, on this system, no. So these are applied. So the reactive or reaction moment, okay, so that is different from applied moment or couple, ha. Okay, so we can also apply couples or moments in a system. Okay, so again, that is different to the reaction moment. Okay, so these are the different types of loadings, okay, that we will frequently see, okay, in the beams and force systems na we're going to talk about here in this topic. So we will start solving sample problems now. So for sample problem number 1, a beam simply supported at ends carries a concentrated load of 300 pound and a uniformly distributed load weighing 100 pound per linear foot. Determine the beam reactions. Okay, so as we can see here, okay, so we have here a beam. Okay, so this beam carries two loads, no? So it carries a concentrated load here. So this is a 300-pound concentrated load, and it also carries a uniformly distributed load, and the weight of this uniformly distributed load is 100 pound per feet. Okay, so we can solve for the equivalent point load or concentrated load of this uniformly distributed load. We're just going to solve for the area of this rectangular load, no? So its area will just be base times height. So its base will be 6 and its height will be 6 pound per feet. Okay, so if you multiply 100, okay, by 6, 100 pound per feet, if you multiply that to 6 feet, okay, feet will be cancelled and what will remain will be pounds. So that will be the unit for a point load, right? Okay, so and after that, okay, so class this beam, okay, so this is actually supported by a roller here at point A and a hinge here at point B. Okay, so we're going to draw the free body diagram of this system. Okay, we have to show the reaction forces that are provided by this support. So let's start solving this problem. So again, we are asked here to solve for the reactions at A and B. So at point A, okay, so the support here, okay, is a roller. Okay, so the reaction force that this roller will provide, okay, to this beam, okay, will be a normal force, right? So it will be a normal force, okay, and it will be um, perpendicular to this surface, no? So this is a horizontal surface. So the reaction here is just a vertical reaction, no? So since this is a roller, so it will only provide one reaction force, no, which is perpendicular to this surface to the point of contact of and it will be applied to the at the point of contact of this roller and the surface. Okay, and also here at point B, okay, so it is supported by a hinge. Okay, so since this is a hinge, okay, it will actually provide two reaction forces. So that will be one horizontal and one vertical reaction, no, here at point B. So let's draw now the free body diagram of this beam AB. Okay, so this will now be its free body diagram. So we have here the concentrated load here, okay, which is 300 pound. And we already resolved this uniformly distributed load into its equivalent concentrated load, okay, which is just the area of this rectangular load, no? So that will just be 100 pound per feet times 6 feet, its length, no? So feet will be cancelled and it will give us 600 pounds. So it will be applied at the center, okay, at the mid-span of this distributed load, which is 3 meters, no, 3 feet rather. That will be its location or position, okay. And now for the reaction forces, so at point A, so again we have here one reaction force. So we will name it as RA. Okay, and point B, okay, so again, there will be two reactions here since this is a hinge. Okay, so there will be one horizontal reaction, and we will name it as BH, no? And there will be a vertical reaction, and we will name this as BV. Okay, but the thing here, class, is that when we sum up forces horizontal here, okay, and we equate that summation to 0. Let's say summation of forces horizontal is equal to 0. Okay, so as we can see here, there's only one horizontal force here. So that is only BH. So there's no other horizontal force here, right? There's no there's no another horizontal loading here. So both loading here are vertical forces, no? And there's no another reaction force that is horizontal. So meaning to say, if we sum up forces horizontal, this BH will just be equal to 0. So we can say that that BH is equal to 0. So we can remove that now from the free body diagram of our system. So as we can see here, we have here reaction at A and just a vertical reaction here at point B, no? Okay, so from here, from this free body diagram, we can now start solving this by using the equations, okay, that we can generate. So again, from our discussion, we can use two equations here, no? It can be either a combination of one moment equation and one summation of forces, or two summation of moments. So in this case, no, we will start solving this by using a moment equation. So we will start by summing up moment at point A. Okay, so summing up moment at point A is equal to 0. Okay, so our assumption here, positive for clockwise rotation. So RA will have no moment about point A since it will pass through point A. So this load, so we will start with this load. So this is 300 pound. Okay, and its moment arm, if we will solve for its moment about point A, its moment arm will be 2. So this will become 300 times 2, and its rotation about point A will be clockwise. So it will be positive here. Now for our 600 pound concentrated load here, so its moment arm about point A will be, so this is located 3 feet from here, plus 2, plus 2, so that will be 7. So that will be 600 times 7, and its moment, its direction, no, of this moment will be clockwise as well, so it will be positive here. Okay, now for the last force here, no, so this is the reaction force at B, so this is BV. So its moment about point A will be BV times its moment arm, which is 6 plus 2 plus 2. Okay, so that will be 10, and its rotation about point A will be counterclockwise. That's why it will be negative here. So it will be equal to 0. Okay, so solving for BV, so only BV is unknown here. So we will input this in our calculator. So this will just be 300 times 2 plus 600 times 7. We will transpose BV, okay, negative BV times 10 to the other side. So it will be positive BV over 10. And to solve for BV, we will just divide what we solved from 300 times 2 plus 600 times 7. We will divide that by 10. Okay, and the answer for this will be 480 pounds. So from here, we already solved the reaction at point B, no, and that is 480 pound, no, for the vertical reaction at point B, no. Now for the another force, reaction force here that we need to solve, we can use another equation. Also, let's say that we're going to use summation of forces for this, no, to solve for RA. So using summation of forces vertical is equal to 0. Okay, our assumption is positive for upward forces. Okay, so we will start with RA. So RA will be positive since it is directed upward, minus 300 since it is directed downward, minus 600 since it is directed downward, and we have here plus BV. Since we have already solved for the value of BV, we will just substitute that. So this will become RA minus 300 minus 600 plus 480 is equal to 0. So we can now solve for RA since only RA is the unknown here. So solving for RA, we just transpose negative 300 minus 600 plus 480. Now we will transpose that. So that will be 300 plus 600 plus 480. And it will give us 1,000. Mali. Okay, so it will give us 420 rather, 420 pound. Okay, so that will now be the reaction at point A. So again, class, these are already the answers, no? But yun nga, again, we can actually use another equation, no? Instead of using summation of forces vertical is equal to 0, we can use actually another summation of moment, no? So we can sum up moment at point B. So summing up moment at point B, okay, so it will just be the moment of RA about point B, that will be RA times 10. Okay, and its direction, okay, or rotation about point B is clockwise, so it will be positive here. Then we have here 300 times its moment arm, which is 8, and its rotation will be counterclockwise, that's why it's negative here. And we have here 600 pounds, so its moment about point B is 600 times 3, and its rotation about point B is counterclockwise, that's why it will be negative here. And it will be equal to 0. So solving for RA, okay, so that will be 300 times 8 plus 600 times 3. So we already transposed 300 times 8 and 600 times 3 to the other side. That's why it became positive. So divided by 10. Oh, so that will be 420 pounds. So it is the same answer, okay, when we use summation of forces vertical, no? So either of these two, okay, you can use summation of forces or summation of moment. So this is uh, mentioned in our discussion that when you are solving systems of or equilibrium of parallel force system, you can use combination of one moment equation, then one summation of forces, or you can use two moment equations, okay, at moment at different points, no? Ayan, so it's up to you what you're going to use. So what's good here is that you can use the other equation for checking. So you can use that for checking, no? So that you can be sure, okay, that your answer is correct, no? But then again, if it's a quiz, okay, or an assessment, no, so no need to show both of the equation here, no. So you can show either summation of forces or summation of moment, no, for the another equation that you have to use to solve this problem. Okay. Okay, so for number 2, determine the reactions R1 and R2 of the supports of the beam loaded with a concentrated load of 1,600 pound and a load varying from 0 to an intensity of 400 pound per feet. Okay, so for this problem, okay, so the free body diagram is already given actually. So this given system is actually a free body diagram, no, since the reaction forces, okay, are already provided here. So we don't need anymore to analyze, okay, what reaction forces are provided by the support, since the reaction forces are already given here, no? So we have here two reaction forces, no? So reaction force R1 and reaction force R2. So this beam, it carries a 1,600 concentrated load and a load varying from 0, intensity of 0 to 400 pound per feet. So we can solve this, no, by using two solutions, no. So the first approach is that as we can see here, this beam carries another beam. So this is another beam, right? So this another beam, it carries this varying load, right? So what we're going to do for the first solution is that we're going to solve first, okay, the free body, or construct the free body diagram of this upper beam, no, that is supported, okay, by this beam, no, by this lower beam. So if we construct its free body diagram, we can see that it carries this varying load, okay, and we can solve for its reaction here. So this is supported by a roller, no, okay. So we will solve for its reaction force due to this applied load, and after that, that reaction force that we solve from the free body diagram of this upper beam, we are going to transfer that here at the lower beam, okay, and that those reaction forces, it will be it will be transferred, okay, opposite with opposite direction, okay, here in the lower beam, no, because this lower beam, okay, this will actually carry this upper beam, no. So of course the loading, okay, that is carried by this upper beam, it will just be transferred here at the lower beam, no. So for the second solution, we can actually directly solve for the equivalent point load of this triangular load, and directly apply that here at the lower beam, no? So we can also do that. So we will see in those two solutions, okay, that it will give you the same result, no? So we will start now with our first solution. Okay, so solving for this parallel force system using solution 1. So we're going to construct first the free body diagram of the upper beam. So for the upper beam, okay, so it is supported by a roller here, okay, and a roller also at the other end, no? So it will just provide one reaction force, and that will be a vertical reaction, okay, and we will name it as RA, the reaction here. Okay, at this point, so we will name it as RA, and the reaction here, we will name that as RB. And we're going to solve for RA and RB. So we can apply here the equilibrium for parallel force system. So we can use two equations. So we can use summation of moment at point A. So our point A is here. Okay, and the forces that will have moment will be 2,400. So by the way, we will resolve this triangular load, no, into its equivalent concentrated load. So that will just be the area of this triangular load, no, and its area will just be 1/2, okay, 1/2 base times height. Okay, so that will just be 1/2 times its height, so that will be 400 pound per feet, times its base, no, so that will be 12 feet. So feet will be cancelled, and it will give you input that in your calculator, 1/2 times 400 times 12, that will be 2,400 pound. Okay, so this concentrated load, okay, so as we have discussed, okay, from our previous discussions, okay, so this equivalent point load, okay, it will be applied, okay, if from the tip of this triangular load, no, it will be two-third of the length of this triangle. So that will be two-third times 12. Okay, it will be two-third times 12 from here. Okay, and if it's measured from the other side, from the vertical side of this triangle, so it will just be 1/3 of 12. Okay, so from that, okay, so we can now solve for the moment at A. Okay, so it will be equated to 0 since this is in equilibrium. Okay, so your RA will have no moment about point A since it will pass through point A. Now for this 2,400 pound concentrated load, its moment about point A, okay, it will be 2,400 times its moment arm. So its moment arm from here to here, again, this is two-third of 12. What is the two-third of 12? Two-third, input that in your calculator, that will be 8. So its moment arm will be 8, and its rotation about point A will be clockwise. That's why it will be positive here. Now for RB, its moment about point A will be RB times 12. Okay, so that will be RB times 12, and its rotation about point A will be counterclockwise. Now that's why it will be negative here, and it will be equal to 0. So we can now solve for RB. Okay, so solving for RB, it will be 2,400 times 8 divided by 12. So we transpose already RB times 12, no? So that it will become positive. So the answer for RB will be 1,600 pounds. So this will now be the reaction at B. Now, to solve for the reaction at A, okay, for the reaction at A, we will take moment at point B, okay, or you can also sum up forces vertical, no? So it's your choice. So in this case, we will use summation of moment at point B. Okay, so summing up moment at point B, so RB will have no moment since it will pass through point B. So the moment of RA about point B will be RA times 12, and its rotation about point B will be clockwise. That's why it will be positive here. Now for the moment of this 2,400 concentrated load, so this will be 2,400 and its moment arm. So again, this moment arm, this distance from the position of this point load to the vertical side of the triangle, it will be 1/3 L, or 1/3 of 12. What is the 1/3 of 12? That is actually 4. Okay, so its moment arm will be 4, and its rotation about point B, it will be counterclockwise. That's why it will be negative here. And we will equate this as 0, to 0. Now, so solving for RA, so that will just be, we just transpose 2,400 times 4 to the other side. So that will be 2,400 times 4 divided by 12. So that will give you 800 pounds. So this will now be the RA. So class, do not box these answers, no? So these are not the items that we are solving here. So we are solving for R1 and R2, not for RA and RB. Okay, so we just solved for RA and RB because we're going to transfer this reaction forces, okay, at the lower beam. No? So redrawing now, okay, or constructing now the free body diagram of the lower beam. Okay, so this is the lower beam. So it carries 1,600 pound load, and at this point, okay, so this reaction force at A or RA, it will be transferred at this same point, no? So this will be RA, and our RA is 800 pounds. So since we transferred this RA, okay, from the free body diagram of the upper beam to the free body diagram of the lower beam, it will be transferred here with opposite direction. So it will be directed downward here, since from this free body diagram, it is directed upward, no? So also for your RB, so RB is here, so it will be transferred also to the free body diagram of your lower beam. So that will be 1,600 pounds, right? So your RB is 1,600 pounds. So it will be transferred here. So from here, we can now solve for R1 and R2 by using two equations, no? That can be one moment equation and then one summation of forces, or two moment equations, no? So let's start solving this. Okay, so this is the free body diagram of the lower beam. So we're going to use summation of moment at the position or at the point of application of R1. No? So this will be that moment. Now we will take moment here. Okay, so taking up moment here at this point. Okay, so R1 will have no moment since it will pass through this point. Okay, and the moment of 1,600 pound, that will be 1,600 times 3. Okay, so its rotation about this point is clockwise. That's why it will be positive here. Now for this RA, this is 800 pound. Okay, and its moment about this point will be 800 times 3 plus 1. Also, that will be 4, no? So its rotation about this point will be also clockwise. That's why it will be positive here. Now for this 1,600 pound, its moment will be 1,600 times 12 plus 1 plus 3. Okay, so that will be 16, no? Its moment arm will be 16, and its rotation will be clockwise. That's why it will be positive here. Now for R2, so its moment about this point is R2 times 16. Okay, and its rotation will be counterclockwise. That's why it will be negative here, is equal to 0. So solving this, we can solve for R2. So we just transpose R2 times 16 to the other side, no, so that we can solve for R2. So this will just be 1,600 times 3 plus 800 times 4 plus 1,600 times 16 minus R, so we transpose that already, divided by 16. So that will be 2,100 pounds. So this will now be the answer for R2, no? So we are asked to solve for this, no, in the problem. So we can now box it. No, and for the other unknown, okay, unknown reaction force, which is R1, we can use summation of forces vertical or summation of moment at R2, no? So either of those two equations you can use. So for this, we will use summation of forces vertical. So summing of forces vertical, that will just be R1, so upward, that's why it's positive here, minus 1,600 since that is downward, minus 800 since that is downward, minus 1,600 since that is also downward, plus R2 since it is upward, now is equal to 0. Okay, so from here, we can solve for R1 because we already solved for R2, no? So we just substitute 2,100 to R2. So solving for R1, that will just be, we transpose this, no? Everything, no? And so what will remain here in the left side will just be R1. Okay, if we transpose all the terms here. So that will be 1,600 plus 800 plus 1,600 minus 21 since we transpose it now to the other side. So that will be 1,900 pounds. So that will now be the answer for reaction 1, no, or R1. So this will now be the answers for this problem. So also, again, you can sum up moment, no, at R2 so that you can check if this R1 is correct, no. So you can use that for checking. So we can also use solution 2 to solve this problem. So for our solution 2, we can resolve directly this triangular load, no, into its equivalent concentrated load. Okay, so this will be the um, resolved, no, concentrated load of this triangular load. And we can actually apply principle of transmissibility here. Okay, that this force, okay, applied here, okay, if we apply the principle of transmissibility, it will, it will, it can be, no, it can be applied directly, okay, in this lower beam, no. So we just apply that principle, okay, and after that, no, so we can now start solving, no. So using the two equations that we can generate, okay, from equilibrium of parallel force system. So let's say we start summing up moment at R1. So we will sum up moment at this point. Okay, so R1 will have no moment. Okay, so 1,600 pound, its moment about this point will be 1,600 times 3, and its rotation will be clockwise. That's why it will be positive here. Now for this 2,400 pound equivalent point load, so its moment about R1 will be 2,400 times its moment arm. So its moment arm, okay, so the position of this point load, no, will be from the tip. Here is the tip, no, from the tip of this triangle load to the position of that concentrated load. That will be 2/3 of 12. So that will be 2/3 of 12. That is 8, no? 2/3 of 12 is 8. Okay, so we will add, so that 2/3 times 12 will just be this distance, no? So the distance that we need, the moment arm that we need is this 2/3 L up to this R1, no? So we will add 1 and 3. So that will be 2/3 of 12, which is 8, plus 1 plus 3. So that will be 12. Okay, so that will be the moment arm of this 2,400 pound concentrated load about this point, no? Ayan, and its rotation will be clockwise. That's why it will be positive here. Now, for R2, okay, so for R2, its moment about this point is R2 times 16. So 16 will be the moment arm, and its rotation will be, what will be its rotation? It is actually counterclockwise. That's why it will be negative here. And it will be equal to 0. Now, solving for R2, so we just transpose R2 times 16 to the right side. Okay, so this will be 1,600 times 3 plus 2,400 times 12 divided by 16. So that will be 2,100 pounds. So that will be the value of R2. So this is the same answer, okay, that we obtain using solution 1. So this is much easier, right? So this solution is much easier. It's a shorter solution, no? Ayan. And also, for R1, we can use summation of forces or summation of moments. So in this case, we're going to use summation of forces vertical. So that will just be R1 minus 1,600 minus, no, this is wrong. So this is 2,400, no, instead of minus 800 plus minus 1,600. This is minus 2,400 plus R2 is equal to 0. So solving for this, okay, so our R2 is 2,100. So our R1 will be 1,600, okay, plus 24 minus 21. What will be the answer for that? That will be 1,900 pounds. So your R1, Okay, your R1 will be 1,900 pounds. So this will now be the answers for R1 and R2. So you can use summation of moment at R2 for checking. No? And also, class, I forgot to mention that you can also check, okay, your answers if it's correct, if they are correct, okay, by summing up, okay, these two reaction forces. If you sum up these two reaction forces, it should be equal, okay, to the total, okay, or to the sum of the applied load. So the applied load actually is 1,600 plus 2,400. So if you sum them up, that will be 4,000, right? That is 4,000 pounds. And if you add R1 and R2, that is 2,100 and 1,900, it should also be 4,000 pounds to say that it is correct. Okay, so from here, we can actually see that 2,100 plus 1,900 is also 4,000 pounds. So in this case, this solution is, these answers, okay, are correct, okay, based on that checking. Okay. So again, the reaction forces, of course, it should be equal, okay, to the applied forces, and it should be opposite in direction. They should have opposite direction. So that's actually a fundamental concept, okay, about this, no, about this topic. We will proceed now to sample problem number 3. The upper beam in the figure below is supported by a reaction at R3 and a roller at A, which separates the upper and lower beams. Determine the values of the reaction. So here, we have here a lower beam or an upper beam. No? So this is the upper beam. So this upper beam, it is supported by R3 here. Okay, and it is supported by a roller here at point A, no? So this separates the this upper beam and lower beam, no? So your lower beam, okay, this lower beam, it is supported by R1 and R2. So we're going to solve this system, no? Parallel force system. For this problem, we are asked to solve for the reaction forces R1, R2, and R3. So as you can see here, we have here three unknown reaction forces. Okay, so we can actually just generate two equations, right? It's just a moment equation or and one summation of forces or two moment equations. Okay, so in this case, okay, so since we have here three unknowns, okay, we cannot solve directly, okay, for these reaction forces. So what we need to do here is solve first, okay, for the free body diagram of the upper beam. If we construct the free body diagram of the upper beam, we can see here that it is supported by R3 and we will have here a reaction force at point A. So this is supported by a roller at point A, so it will provide one vertical reaction, right? Okay, and from that, that the unknown for that free body diagram will just be RA and R3. So we can solve for RA and R3. So after solving for RA, we can transfer that reaction force at A here at the lower beam. Okay, so it will be transferred with opposite direction. Okay, and from that, okay, the unknown, okay, in the free body diagram of the lower beam will just be R1 and R2. And from that, we can solve for R1 and R2. Okay, so again, for our solution, so let's solve first or construct first the free body diagram of the upper beam. So we have to solve first the free body diagram of the reaction forces in the free body diagram of the upper beam. So this will be the free body diagram. So this is the upper beam. Again, this is supported by R3 at this side, no? And at point A, it is supported by a roller. So it will provide RA, no? So we will name that reaction force as RA. Okay, so from here, we can actually solve for RA and R3. So let's sum up moment at point A to solve for R3, no? So RA will have no moment at point A since it will pass through point A. Okay, so for 600 pound force, its moment about point A will be 600 times its moment arm. So its moment arm, so this moment arm will just be, let's analyze this, no? So this beam, no? So this is actually 14 feet, right? So this is 14 feet. If this is 10 feet, so meaning to say, this distance is 4 feet also. So the moment arm of 600 pound is 4 feet. So its moment will be 600 times 4, and its rotation about point A will be counterclockwise, no? That's why it will be negative here. Now, for 1,900 pound, its moment, okay, about point A, we know that this is already 4, no? So this remaining distance will be 6. Okay, so the moment arm of 1,900 pound, about point A will be 6, so that will be 1,900 times 6. And its rotation about point A will be clockwise, that's why it will be positive here. Now, for R3, so its moment about point A will just be R3 times 10, and its rotation will be counterclockwise, so it will be negative here. And this is equal to 0, so we can directly solve for R3. So solving for R3, okay, so this will be, we just transpose R3 times 10 to the other side, so it will become R3 times 10. No? So solving for the terms here in the left side, that will be negative 600 times 4 plus 1,900 times 6. So divided by 10 to solve for R3, and that will be 900 pounds. So this will now be the answer for R3. So you can actually box this since we are asked to solve for the reaction force R3, no? So you can already box this. And to solve for RA, so we can sum up forces vertical or sum up moment at R3. So it's your choice. So here we're going to use summation of forces vertical. So is equal to 0. So upward forces are positive. So this will be RA. So it is positive since it is directed upward. Minus 600 since it is downward. Minus 1,900 since it is downward. Plus R3 since it is upward. So that will be equal to 0. Since we already solved for R3 and that is 900 pounds, so we will just substitute that. Okay, and solving for RA, that will just be 600 plus 1,900 minus 900. So we transpose already, no? So that we can solve for RA. So that will be 1,600 pounds. So this will be the RA. So no need to box this because it's not asked from the problem, no? So we just have to solve for R1, R2, and R3. Okay, so we will just need this RA. Okay, we will just need this to solve for the remaining reactions R1 and R2. Okay, so constructing now the free body diagram of the lower beam. So this is the lower beam. So the reaction at A from here, okay, so it will be transferred at the free body diagram of the lower beam. And since it is directed upward here, so in the free body diagram of the lower beam, it will be directed downward. So the obtained RA is 1,600. So this will be 1,600 pound, and it will be directed oppositely, no? Ayan. So it will be directed downward here. Okay, so from here, from this free body diagram, since we already have two equations or two unknowns here, which are R1 and R2, we can now solve this using two equations. Okay, solving now for the free body diagram of the lower beam. Okay, so we will sum up moment at R1. Okay, so summing up moment at R1, so R1 will have no moment since it will pass through that point. So the moment of 4,000 pound about this point will be 4,000 times 4 and it will be clockwise, so it will be positive here. And then the moment of R2 about that point will be R2 times its moment arm, which is 10. So that will be R2 times 10, and its rotation will be counterclockwise, so this will be negative here. And for RA, which is 1,600 pound, its moment will be RA times its moment arm, which will be 14, no? 4 plus 10. Okay, and its rotation about this point will be clockwise. That's why it will be positive here. And this will be equal to 0. So again, RA is already 1,600. So solving for R2, that will just be 4,000 times 4 plus 1,600 times 14. So we transpose R2, negative R2 times 10 to the other side. So it will become positive R2 times 10. No? So this will be divided by 10 to solve for R2. So this is divided by 10. So this will be 3,840 pound. Okay, so in this case, this will already be the answer, no? So we are asked to solve here for R2 as well. So you can box that now. Now for the remaining unknown reaction force, so we can sum up forces vertical. So that will just be R1 since it is upward minus 4,000 since it is downward plus R2 because it is upward minus 1,600 pound since it is downward. Okay, and that will be equal to 0. So solving for R1, we already have RA, that is 1,600. Okay, so solving for R1, so that will be, we transpose 4,000 minus 3,840 plus 1,600. So that will give you 1,760 pounds. So this will now be the R1. So to solve for R1, you can actually use also moment at R2, no? So you can also do that, okay, to check. And also, to check this further, okay, so we can also check if the reaction forces that we obtain are correct by summing up these reaction forces. So, our R3, what's the value of our R3? So anyway, the total of our applied forces will be 4,000 plus 600 plus 1,900. That will be 6,500, no? And if we sum up our reaction forces, that should be equal to the applied forces. So 3,840 plus 1,760 plus the reaction at 3 or yung R3, no? Or R3 is actually 900. So that will actually give you 6,500 pound also. So these answers are logical since it is equal, okay? These reaction forces are equal. The sum of these reaction forces are equal to the total applied force, no? So this is correct, no? We can assume that this is correct. So now let's proceed to sample problem number 4. So we have to solve for the reactions at the support of the given beams with fixed support at one end. Okay, so here we can see here that all these beams, no, they are all fixed supported at one end. Okay, so we're going to solve the reactions for each beam. Okay, so for letter A, this is for letter A, for letter B, and for letter C. So we will solve each and every beam here. Okay, so for the beam A, okay, so for the first beam, so we will draw the free body diagram of the first beam, no? So this is the first beam. So it is fixed supported here at one end at point A. No, so drawing its free body diagram. So as we know from our discussion about the different supports and the reaction forces that they provide. Okay, so for fixed support, we know that there are three reaction forces or reactions, no? So there will be a horizontal and vertical reaction, and there will also be a reaction moment or moment reaction. Okay, so this will be the three reactions for fixed support, no? So constructing the free body diagram of this beam. So this will be the beam, no? The free body diagram of the beam. So for the reaction that this support provides, so we have here vertical reaction, horizontal reaction. So we will name them as AV and AH, and also we have here a reaction moment. Okay, and we will name it as MA, no? So we can actually assume the direction of that reaction moment, but we can base our assumption from the loadings applied. Okay, so as we can see here, these loadings, 4 kilonewton and 2 kilonewton, if we take the moment, okay, take the moment of 4 kilonewton and 2 kilonewton about point A, it will actually give a counterclockwise rotation, right, about point A. So it is counterclockwise. So if the moment, okay, that is produced, okay, or caused by these applied forces is counterclockwise, so the reaction moment should oppose that. Okay, if these applied loads will produce a counterclockwise moment about point A, so this reaction moment about point A, it should be opposite that direction. So it should be clockwise. That's why our assumption here is clockwise. So this is actually a malapit sa katotohanan na assumption. Okay, so our assumption here is clockwise for the reaction moment at A. So we're going to solve for these reactions. Okay, so actually for AH, as we can see here, there is no horizontal loading. So there will be no another horizontal force that we can include in the summation of forces horizontal, no other than AH. So apparently, no AH will just be equal to 0. So you don't need actually to show this in your solution, no? So I just put here this summation of forces horizontal, okay, just for you not to get used, okay, to not solving it. Baka kasi masanay ka that you don't solve for the horizontal horizontal forces, no, or the summation of forces horizontal. So I just put it here, but you don't really need to put it here because obviously this will just be equal to 0. Now to solve for AV and MA, so we can use two equations that can be summation of forces vertical and summation of moment, no? So we can start with the summation of forces vertical since we only have here one unknown vertical reaction force, no? So we can directly solve for AV. So summing of forces vertical is equal to 0, positive for upward forces. So this will just be this force, 4 kilonewton, it will be downward, so it will be negative here. 2 kilonewton, this is downward, so it will also be negative here. And your AV is upward, so it will be positive here, is equal to 0. So our AV here will be 6 kilonewton. So if the answer here is 6 kilonewton, meaning to say our assumption for AV is correct, that it should be upward. Okay, so obviously, since all the forces, applied forces are downward, so your reaction force should be upward. Okay, so in this case, we have that, we have assume it right, no? So AV is 6 kilonewton upward. Okay, so this can be boxed already since this is already an answer, no? So this is a reaction at this support, no? And also, for the moment at A, no, for this reaction moment A, okay, so we can sum up moments at point A. Okay, so this MA, this reaction moment, okay, we will just include this, okay, in our summation of moment. Okay, so this is just like our concept about couple, okay, that if we sum up moment at any point, it will be included. Okay, so this is already a moment. So summation of moment at A. So the forces that will have moment will be 4 kilonewton and its moment arm, 4 kilonewton, its moment arm about point A will be 4, right? So this is 2 plus 2. And its rotation about point A will be counterclockwise. That's why it will be negative here. Now for the 2 kilonewton force here, its moment about point A will be 2 times its moment arm, which is 2. Okay, and its rotation also is counterclockwise, so it will be negative here. And we will include in this summation our reaction moment, which is MA. No, so our assumption here is clockwise, so it will be positive in our summation. So that will be plus MA is equal to 0. So we can now solve for the reaction moment at A. No, so your MA will just be equal to, so we solve this, we transpose negative 4 times 4, so that would be positive 4 times 4. And we also transpose negative 2 times 2, so that will be plus 2 times 2. Okay, and it will give you 20 kilonewton meter. So the unit for this is kilonewton meter. Kilonewton per meter atay nabanggit ko. So that is kilonewton meter. Okay, so that will be the reaction moment at A. So this will now be the answers for letter A. These are the reactions, okay, at the fixed support. So to solve for the second beam, so this is the second beam. So we will construct the free body diagram of this beam B, no? Okay, so it is also supported by a fixed support here at point A, no? So we will draw its free body diagram. So again, its free body diagram, okay, for the reactions that are provided by this fixed support. So there will be 3 reactions here. So there will be one vertical reaction. We will name it as AV. We also have here one horizontal reaction and we will name it as AH. And we also have here a reaction moment and we will name it as MA. So we will just assume that it is clockwise. So in this case, we are not sure yet, okay, if what will be the direction of reaction moment, no, of this reaction moment, since we have here a force that is clockwise, no, about point A, its moment, no, and its moment will be counterclockwise, no. So we don't know what will govern here. Okay, so we will assume here that the reaction moment at A will be clockwise, no. So we will just assume it this way, no. So it can be proved right naman, no, along our solution, no. So if the answer is negative, so meaning to say our assumption is wrong. Okay, so we will start solving for the reactions here. So obviously AH will become 0 since there are no other horizontal forces involved here other than AH, no? Okay, so AH will clearly be just equal to 0. And for the AV, no, so we can solve that using summation of forces vertical. So we can directly solve for AV since there are no other unknown vertical forces, no, other than AV. So we just sum up forces vertical is equal to 0. So upward forces will be positive. So this will just be 900. So that is positive since it is upward. Minus 1,600 since it is downward. And by the way, no, I forgot to say that this uniformly distributed load, we will resolve this into its equivalent point load. So its equivalent point load will just be the area of the rectangular load, this rectangular load. So this will just be base times height. Okay, and it will just be 200 pound per feet times its length, which is 8 feet. Okay, 8 feet the length of this rectangular load. So that will just be 200 times 8 feet. That will be 1,600 pounds. And it will be applied at the mid-span or at the center of this uniformly distributed load, no? And it will be 4 feet. Tama? It will be 4 feet from both sides, no? It will be 4 feet from here and 4 feet from here. Okay, so I just forgot to mention that, no? So again, for summation of forces vertical, that will just be 900 minus 1,600 plus AV since it is upward, no? So it will be equal to 0 and we can solve for AV. So the AV here is positive, okay, since it will be negative 900 plus 1,600 since we will transpose them. Okay, and it will give you 700. Now, it's positive, so meaning to say, our AV, we assumed it right, no? So this is really upward, no? So this will be the answer for AV. Now, for the reaction moment, so we can take moment at point A to solve for the reaction moment A, no? Okay, so we will take moment here at point A. So AV will have no moment at point A since it will pass through point A. Okay, so for this 900 pound force, no, so its moment about point A will be 900 times 6. And its rotation will be clockwise. So it will be positive here. Now for this 1,600 pound force, so its moment about point A will be 1,600 times its moment arm, which will be 4. So that will be 1,600 times 4, and its rotation will be counterclockwise, so it will be negative here. And then we will just include the reaction moment, MA, here in our summation. So our assumption is clockwise, so it will be positive here in our summation. So it will be equal to 0, so we can solve for MA. So that will be, we will transpose 900 times 6, so that will be negative 900 times 6 plus 1,600 times 4. So we transpose those values. So MA will be 1,000 pound-feet. Okay, so this will now be the reaction moment about reaction moment of the fixed support, no, at point A. Okay, so you can now box this answer. Okay, so we will now proceed to the third beam here. So this is the beam C. Okay, so let's construct first its free body diagram. So the free body diagram of that beam. Okay, so since this is fixed supported here, so it will provide 3 reactions. So it's horizontal and vertical reaction, AV and AH, and we also have here a moment reaction. So again, we will just assume the reaction moment at A as clockwise, no? So that's our assumption here. And as you can see here in our in the given beam, okay, so we actually have here one horizontal force directed to the left, okay, and reaction force directed to the right rather yung kanina, no, and it will be directed to the left. So this will actually form a couple. Okay, so these are parallel forces, and actually it's already given here that this is a moment or a couple, no? So it's already given here that this is 2 kilonewton meter. So this is a couple. So the direction of this couple, its rotation will be this way. So this is clockwise, no? So we can rewrite this applied couple, no, here. So this is our applied couple. So this is clockwise and this is 2 kilonewton meter. So from here, we can now start solving, no, for the reactions at point A or at at support A, no. Okay. So for AH, again for AH, this will just be 0 since there are no other horizontal forces here, no? So obviously AH will just be equal to 0. Now for AV, so we can just sum up summation or we can just sum up forces vertical, okay, is equal to 0. Okay, so the only vertical force here is 250, okay, and this is downward, so it will be negative here, plus AV, and it will be equal to 0. So solving for AV, so obviously it is upward, right? So since the applied force is downward, so it should be upward, and it is 250 Newton. Now, to solve for the reaction moment, we will take moment at point A. So taking moment at point A is equal to 0. So positive for clockwise rotation. So for this 250 Newton force, its moment about point A will be 250 times its moment arm. This will be 2 meter plus 2 meter. That will be 4 meter. And its rotation will be counterclockwise. So it will be negative here. Now, for this given applied moment or couple, this is 2 kilonewton meter. So, class, you have to be careful here because the given unit here is kilonewton. Okay, so the unit for your load is Newton. So, you have to convert either this Newton to kilonewton or this kilonewton to Newton. So, converting this kilonewton to Newton, so 2 kilonewton meter is actually equal to 2,000 Newton meter. So, that will be the equivalent. So, this is already a moment, so we will just include this in our summation, and this is clockwise. So it will be positive 2,000 here. Okay, so now for the reaction moment, which is MA, so our assumption here is clockwise, so we will just plus MA here, no? We will just add MA here. It is positive since it is clockwise assumption, no? And this will be equal to 0. So we can now solve for MA. So solving for MA, this will actually give us, so we transpose 250 times 4, that will become positive, and 2,000, that will become negative 2,000 if we transpose. So that will give you negative 1,000 Newton meter. So the negative sign here indicates that our assumption is wrong. So for MA, okay, so the right assumption, okay, or the rotation of MA or direction of reaction moment, MA, it should be counterclockwise. So we can redraw that free body diagram, no? So we can correct the direction or the rotation of the reaction moment MA, no? And it should be counterclockwise, no? So this will now be the answers for this problem. These are now the reactions at this fixed support A, no? Okay. Alright, so we will now proceed to frictionless pulley system. Okay, so frictionless pulley means that no force is required to overcome friction from the pulley rotating around its axis. Okay, so let's say that we have here this pulley. Okay, and we have here this cable, okay, that passes through this pulley, no? So, our assumption here is that this pulley, okay, this pulley is frictionless. So, meaning to say, there will be no reaction force that will be provided by the friction, no? So, since it is assumed as frictionless. So, meaning to say, okay, if this force P, okay, put, okay, in this pulley. So if this is force P, so this will just remain the same along this cable, no? So it will also be force P since there will be no effect due to friction, no? So if this is force P here, so as it passes through this pulley, so in this part of the cable, so this is also force P, so there will be no effect, no? So that's the concept of frictionless pulley, no? And also, for frictionless pulley system, force P applied at one end of the cable in the system is constant if the cable is continuous. Okay, so again, no, if we let's say that we apply force P here at the one end of this cable, no, and this is put here in this pulley, no. So along the continuity of this cable, okay, if this cable continues to pass through this pulley, and then it is continuous as it passes through this pulley B, no? So until it is cut here. Okay, so meaning to say, okay, the reaction force, okay, of those cable, okay, as long as it is continuous, if there's an applied P here, so it will just be constant. Meaning to say, if it is P here, so here at this part, this cable, the reaction force here will just be P. The tension force here will just be P. Okay, so as long as it continues here, so this is still P. So this is still P. Okay, up to here. So this is still continuous here. So this is also P. Okay, so this is a very important concept, okay, for this topic, no, that the force P applied at one end of the cable, it will be a constant, okay, if the cable is continuous. Okay, so we will use that concept in solving for problems here in about this topic now. So let's start solving problems. Okay, so this is our fifth sample problem. So find the tension in the cable and the force P required to support the 600 Newton force using the frictionless pulley system. So we're going to neglect self-weight here as mentioned in the problem, no? So there are also cases that the self-weight of the pulleys are given. So we will involve that or include that in our computation, no, if ever it is given, no. So since it is not given here, so we will neglect it. Okay, so again, we are going to solve this, no, using the concept that I've discussed from the previous slide. So let's start solving this. Okay, so for our solution for this, no, so again, we are asked here to solve for the tension in the cable. So this is the cable. Okay, and we are going to solve for force P. Okay, so to solve this, no, so we have to draw the free body diagram of these pulleys, no, so that we can see the tension forces, okay, that will be provided by the cables, no. Okay, so so actually this pulley system, okay, it supports a 600 Newton load here, no, at this end. No, so let's start constructing the free body diagram of each pulley. So we will start with the free body diagram of pulley C. So this is the pulley C. Okay, so constructing its free body diagram. So as we know, this pulley, okay, so we have here a support here, no? So this pulley is supported by this, I don't know if it's a rod or a cable, no? So this is supported by this, no? So this will provide a tension force, no, for this pulley to carry that pulley. Okay, so its reaction force will be upward, no? And we will name it as TC, no, or tension reaction at C. Okay, and also, since we have here an applied load P, okay, so this applied load P, if this is force P here at this end of the cable, if we put here on the pulley, okay, so since this cable is continuous, Okay, so from here, as it crosses or passes through this pulley C, so at this point, if we cut this cable, no, so we will see the tension force that it provides, no. So the tension force that this cable provides, okay, if we show it here, so since this is force P, so along its continuity, it is also force P here. So because it is a frictionless pulley, so there will be no resisting effect of due to friction because it is frictionless. So if this is force P and this is a smooth surface, this is a smooth pulley, no, so this will also be force P. Okay, so that's why it will be force P here. No, so this is also force P. And also class, this pulley also supports pulley B, right? So this is supported. This pulley B is supported by this rod, no? And this rod is actually supported by pulley C. So there will be a um, tension effect here, no? So this will pull down the pulley C, no? So we will name this reaction as TB, no. So this is a tension force at point B, no. So we will draw it this way, no. So this will now be the free body diagram of pulley C. So if the weight of this pulley is given, so we will just apply its weight at the center of this pulley, and it's always downward since it is weight. Okay, but it's not given here. We are told in this problem to neglect self-weight, so we will neglect it. We will not include it in our free body diagram. Now, we need also to draw the free body diagram of pulley B. So for pulley B, okay, so as we can see, I think it's better if we start with the free body diagram of pulley A. So for the free body diagram of pulley A, this is our pulley A. So again, this is force P, no? So along its continuity, it will be constant. So here at this point, this is still P. So as it passes through point A, so this will still be P. Okay, and as it passes through point B, it will still be P since it is still continuous. So meaning to say, these three cables here, okay, that supports this pulley A. So this will be the support, no, of pulley A, these three cables. So this will all be P. Okay, since it is continuous here, this is continuous as it passes through pulley A, as it passes through pulley B. So this is still continuous until it is cut here at this point. So these cables will all provide, of course, they will all provide tension force. They will provide a pull. Okay, and these three tension forces provided by this cable will all be P. Okay, since again, this force P will be constant all throughout the continuity of the cable. Okay, so this will be P here, and this will be P, and this will be P. And this pulley A actually supports a 600 Newton load, no? So it will also be included here in the free body diagram. And now for the free body diagram of pulley B, okay, so as we know, so this is force P, this is still force P until here, and as it passes through here, this is force P. So this will also be force P, and this will also be force P. So this cable, no, the tension force that it provides for pulley B, it will be force P as well, and this as well, no. And there is also a rod that supports this pulley B. So from the free body diagram of pulley C, no, we have already mentioned that. So it will just be it will be upward here, no, since it will support or it will carry pulley B, no. So that will be tension at B, no. And so from here, again, we are asked here to solve for the tensions in the cables and force P. Okay, so to solve for force P, we can actually start from the free body diagram of pulley A, right? So we can directly solve for P since the only unknown here is force P. Okay, so we can use summation of forces vertical, okay, from pulley A, from the free body diagram of pulley A. Okay, we just sum up forces vertical, so positive 4 upward forces. Okay, so um, this will just be P plus P plus P since they are all upward, and minus 600 since your 600 Newton load is downward. So it will be negative here. So it will be equal to 0. So we can now directly solve for P, no? So this will just be 3P minus 600. Okay, and solving for P, that will just be 600. We transpose it, okay, to the other side, divided by 3. So this will just be 200. So this is now the answer for the item that we are solving, no, that we are asked to solve. So this is already force P. So this is 200 Newton. Now we are also asked you to find the tension in the cable. So actually, the tension in the cables are all P, right? Because this cable is continuous. So, because it is continuous, all the its force, okay, the applied load P here will just be constant. Okay, so the tension in the cable is equal to P is equal to 200 Newton. So just in case that that we are also asked to solve for let's say for TC and for TB, so we can also solve them, no? So by using the free body diagram of Pulley B and Pulley C. So using the free body diagram of Pulley B, since we have already solved for the value of P, we can solve for TB. So that will just be summation of forces vertical is equal to 0. Upward forces will be positive. So that will just be TB minus 2P. Okay, and that will be equal to 0. So, substituting P, that is 200, and solving for TB, that will just be 400 Newton. So that will be the TB. No? So this is not asked from the problem. No? So we will not box it. So just in case that it is asked, okay, that it will be asked in the problem to solve for TB. Also for TC, from FBD of Pulley C, we can solve for that tension force. Okay, so we just use summation of forces vertical here. Okay, so that will just be TC minus 2P minus TB. Since we have already solved for TB, which is 400 Newton, and P, we have already solved that. That is 200 Newton. So we just substitute them here. So we can solve for TP. And our TP here is 800 Newton. Okay, so this will now be the TC. No? So again, no need to box this since this is not asked, okay, in the problem. Okay, so let's proceed now to sample problem number 6. So we are asked here to determine the force P that will keep the pulley system in equilibrium. So we will just neglect the weights of the pulley. Okay, so for this system, okay, so we will analyze this now in our solution. Okay, so let's start solving this. Okay, so again, for this problem, we are asked here to solve for the value of P. So this is the P, okay, that the problem refers, no? So this is force P. So we will analyze this system. So again, we will use our concept here that this applied force P, it will be constant along the continuity of the cable. Okay, as long as the cable is continuous, okay, it will be constant P. Okay, so we will draw the free body diagram of each pulley here, no? So that we can analyze this thoroughly, no? So we will start with the free body diagram of this pulley. So this is the first pulley. Okay, so this is force P. So if it is put here in this pulley, okay, so since this is continuous, if this is force P here, so here, it will still be force P. So it will be force P. It will also be force P here. Now, this pulley is actually supported by this, I don't know if this is a rod or a cable also, no? But this is supported by this, no? So, as we know, to support this, of course, it should be a tension force, no? It should be upward so that it can support this pulley, no? So, we will name this as T1. And as we know, this T1, no, it will just be 2P. Since if we sum up forces vertical here, okay, so your T1 will just be equal to P plus P. So that will be 2P. Okay, so now we proceed to this pulley. Okay, so the free body diagram of this pulley will be, as we know, so this is still force P. Okay, so this is still continuous up to here. So this will also be force P. And this is actually continuous up to here. So this will also be force P. And it is actually cut here. Okay, so this is already cut here. The cable is already cut here. So this is no longer continuous here. Okay, but here, as we can see here, So this is P, this cable is P. Okay, if we draw the free body diagram of pulley A, so the supports of this pulley A will be these three cables, no? And this cable, as we know, this will all be P since the cable here is continuous, no? So this will be force P. This will also be force P, and this will also be force P. Okay, so from here, this pulley A actually carries, okay, this ano no, this pulley, no, through this cable, no, so it's carrying that, no, so this will provide um, a downward reaction force or downward force, no, applied force, no. So as we know, that downward force, okay, to keep this pulley A in equilibrium, of course, if we sum up forces here, okay, so this downward force, it should be equal to the upward forces here. So this downward force should be equal to 3p, since the forces that will support this downward force will be P plus P plus P. So it should be 3P here. Okay, so as we know, this cable already carries, or the force already here in this cable, this is not P. Okay, so this is not P because our cable is already cut here. So this is no longer continuous here. But as we know from the free body diagram of this pulley, no, we already know that this is 3P. So this cable, this is already 3P. So along its continuity, it will be constant. Okay, so it will be constantly 3P along its continuity. So this is 3P. So if it is still continuous here as it passes through pulley B, so this is still continuous. So this is still 3P. So this is continuous here as it passes through this pulley. So this will also be 3P. Okay, so drawing for its free body diagram. Okay, for the free body diagram of this pulley. So this is 3P. So this will be 3P here, and this is also 3P. So this will also be 3P, and this will also be 3P, and it carries this 1,800 pound load here, no? So the cable here is cut already here, no? So again, this pulley B is carrying 1,800 pound load. So as we can see here, no, we can actually start solving for P, right? From this pulley, from pulley B, right? From the free body diagram of pulley B, we can directly sum up forces vertical, and since P is the only unknown, we can directly solve for P. So from the free body diagram of pulley B, okay, so we will just use summation of forces vertical is equal to 0. Okay, so upward forces will be positive. So this will just be 3P plus 3P plus 3P minus 1,800. And we can solve for P here, so that this will become 90 minus 1,800 is equal to 0. So this will just be 1,800. We transpose it, so it will become positive, divided by 9 to solve for P. So this will give us 200 pounds. So this will now be the answer for P. So this is 200 pounds. So this is the item that we are being asked here in this problem. No? So this will now be the answer. So that concludes our discussion. I hope that you learned, and I hope that you attain the learning outcomes for this topic. So for this topic, we have a CM assessment task. So you will answer that assessment task and submit that on our next meeting. So I hope that you enjoyed this discussion. Okay, so happy studying, class. Okay, so just be diligent and persevering, class, in studying this. Okay, so bye-bye. Keep safe. God bless.